Welcome to the Explainer. Today, we're pulling right back the curtain on the invisible architecture that runs, well, pretty much our entire digital lives. Every single time you open your phone, send a quick message, or ask for directions, there is this massive, silent engine working behind the scenes. We're going to uncover exactly how that engine works today, and honestly, it's absolutely fascinating.
Think about the apps you use every single day. Here's a wild truth to kick things off. Google Maps doesn't use arrays to find your fastest route home. Facebook doesn't use simple lists to figure out who you might know. When the biggest tech giants in the world need to solve incredibly complex, interconnected problems, they completely abandon those basic data structures. Instead, they use the ultimate data structure, graphs.
Okay, let's dive right into this. In computer science, a graph is a non-linear data structure. It's essentially just a collection of nodes, which we formally call vertices, that are connected by lines called edges. Unlike simpler structures that just hold data in a straight, predictable line, graphs exist specifically to model multi-directional, messy, real-world relationships.
Explain like I'm 5. Cities and socials.
To really grasp how powerful this is, let's just strip away all the jargon for a second. Linear structures or tree structures have very strict hierarchical rules. There's only one valid path from the top root down to a specific node. But we all know the real world doesn't work like that. The real world is a massive web of flexible, completely unpredictable connections. Graph structures have no specific connection rules, making them the absolute perfect tool to model real life.
Think about a simple traffic intersection. If you're designing navigation software, you literally can't just use a flat list of street names. You model it as a graph. The specific turns you can make are the vertices, or the nodes. The roads connecting them are the edges. By mapping it out this way, an algorithm can instantly calculate which paths are physically possible and, which ones will cause a crash.
All right, before we get into the heavy tech applications, let's quickly lock in the basic anatomy of a graph. First, we have vertices, or nodes, which represent our entities. That could be a city on a map or a person on a social network. Second, we have edges. These are the actual physical or digital connections between those nodes. And third, neighbors, which are simply any two vertices joined directly by a single edge.
Directed versus undirected graphs.
So, to understand how social media algorithms actually function, we have to look at the big divide in network design. First up, undirected graphs. These are symmetric, two-way connections. Think of Facebook. If I'm your friend, you're my friend. It's totally mutual. Then we have directed graphs, sometimes called digraphs. These use one-way arcs with a very specific direction. Think Twitter or X. I can follow you, but you definitely don't have to follow me back. The data flows just one way, from a tail to a head.
So the crucial point here, from a math perspective, is that in an undirected graph, the edge connecting vertex V and vertex W is exactly the same as the edge connecting W and V. There's no arrowhead dictating the flow of traffic. The relationship is inherently a two-way street.
But here's the catch. Those mutual two-way connections scale up into incredibly dense webs of data extremely quickly. Imagine this isn't just a few letters on a screen, but thousands of users or thousands of servers in a massive data center trying to communicate with each other. The sheer volume of relationships becomes absolutely staggering.
Code logic, matrices, and lists. This actually brings up a major problem. How do we teach a completely blindfolded computer to understand these sprawling visuals? Well, the first method is the adjacency matrix. We list our vertices on the rows and again on the columns. To tell the computer an edge exists between vertex 0 and 1, we just drop a 1 in that cell. If there's no connection, we leave a 0. It's basically just a massive spreadsheet of true or false check marks.
But the adjacency matrix has a pretty massive trade-off. Yes, it's incredibly fast. The computer can instantly look up a row and column and know if a connection is there. But it requires memory space for every single potential edge. So if you have 1 million users, you need a grid of 1 million by 1 million cells, even if each user only has like 10 friends. It's highly computationally expensive and a huge memory hog.
Now, what's really interesting is how we solve that exact memory problem. We use the second method, an adjacency list. Instead of a giant, mostly empty grid of zeros, we just create a simple array of our vertices. Then, each vertex simply points to a linked list of its actual existing neighbors.
The advantage here is phenomenal.
The storage required is only proportional to the actual number of connections. If a node has 0 friends, it takes up 0 space, which is, well, a little sad for the node, but great for our computer. For sparse graphs where not everyone is magically connected to everyone else, the adjacency list is massively space efficient and is basically the go-to for modern tech.
Why graphs rule?
Zooming out for a second, it's wild to think about how these structures basically run our modern world. Graphs are the core of pathfinding algorithms getting you from point A to point B. They are the backbone of social networking, and most excitingly, they are the foundation of graph neural networks in artificial intelligence. Every single time Amazon recommends a product or your bank flags a transaction for fraud, a graph is traversing edges and nodes to find those suspicious patterns or perfect matches.
There's this fantastic quote from our source material that perfectly sums this up. Graphs bridge the gap between structured and unstructured data, allowing AI models to reason about context and connections rather than isolated values. That is the magic right there. Graphs teach computers context. They don't just see a random data point, they see exactly how that piece of data fits into the grand interconnected universe of information.
So the next time you boot up a map or scroll through a social feed, you're going to know exactly what kind of invisible architecture is working under the hood. But it does make you wonder, if an algorithm can perfectly map our cities and our friendships, what part of human behavior will graphs be able to map next? If you found this explainer helpful, drop a like, hit subscribe, and let's get coding. See you in the next one.